Again, welcome to DSRT 734 class, Inferential Statistics in Decision Making. These lectures cover the concept of evaluating the fit of a linear model. Now, to evaluate the fit of a linear model, the main goal is to know the error in the linear model that we created. So the total error, which we can call the variance or the sum square error from our previous lectures. So we said the usefulness of a regression model always depends on the magnitude of prediction errors we expect the model to produce. So if we know the errors that the system or the model will produce, that will be very great. And the goal again is to reduce this error. Also, computing the variation of error data is the same as computing the variation in a data set. We cover this in descriptive statistics. Finding the variance or standard deviation of data set means we want to find out how the data varies, the variation in the data set or the dispersion. Now, the goal in constructing most linear models is to use the independent variable to explain or predict the dependent variable. Now, in this case, an error represents the model's inability to predict the variation in the dependent variable. So we start with the variance of the error. Again, the main purpose of a variance of error is to know the variation of error in the data set. So the former is almost the same as finding the variance in a data set. Here, E will stand for each data error of Y. So from our previous lecture, we say E equal to Y, which is the actual observed value of Y, minus the predicted Y, which will be Y caret. So the sum of it, of the difference of E minus E expected, or the mean, all square, is the same as the sum square error, SSE. So which means the variance of the error will be SSE divided by n minus 2. Again, n is the sample size. Also, we can find the total sum of squares. From our previous lectures, we say the total sum of squares will be Y minus Y average, or square and the sum. So if the data set is 10, then we're going to find the difference of Y minus Y mean 10 times square and then add them together. We also have to know the coefficient of determination. Normally, the coefficient of determination measurement will summarize the degree of fit of the linear model on a standard scale. So here we say the proportion of variation explained by the model is called the coefficient of determination, and it's denoted as R square. Normally, if we know the value of PSC correlation R, when we square it, then that will give us the percentage of the independent variable that determine the dependent variable. So we say the proportion of a variation explained by the model is called the coefficient of determination. And also the actual formula here will be SSR divided by total SS, or 1 minus SSE divided by total SS. Always the coefficient of determination is the same as PSC correlation. The values are between 0 and 1. Actually, with the PSC correlation from -1 to 1. Since we are looking for R square, we will never get a negative value, because anytime we get, let's say, -0.5, any value negative square will be positive. So always the coefficient determination value is between 0 to 1. And the PSC correlation is from -1 to +1. Now, if the value is 0, it means the percentage of the data that determine the Y When I say data, I mean the independent variable, determine the dependent variable is 0%, which means none of them determine it. And but if it's close to 1 or 1, then we say 1 will be perfect. That means 100% of the independent variable determine the dependent variable. So we have example here. Here we have an SAT that has been used for years as a predictor of academic success. So if SAT scores are predictors of academic success, they should be positively related to grade point average upon graduation. Now, 27,000 graduates of a state college were sampled, and their GPA upon graduation and SAT score reported upon admission are recorded as a pair data values in the following data. So pair data value means we have two variables. So these are the students. This is their SAT score and also their college GPA and then predicted GPA. So since we were able to, in order to find the predicted GPA, we have to create a model. We will create a model based on the SAT score and their actual GPA. So since we know creating a model, we can't get it 100% correct. This is the errors that we generated. We square the errors also. So let's say this data is 22 students. We have up to 30 students here. So the first thing we should do, let's plot a scatter plot. From our previous lectures, we said scatter plot is a quick way to find out if there's a pattern in the two variables, if they have any association. So this is our graduating GPA score. This is the dependent variable. It will be vertical. Then horizontal will be total SAT score. So total SAT score will determine the student's GPA or graduating GPA. Now, based on the scatter plot, we can see an increasing pattern, but not too perfect, because no matter where we draw a straight line fit, majority of the points will not be around the line. So our value will be a little bit lesser. That's for the R value. So here we say the scatter plot of the data suggests that as SAT score increase, the GPA tends to increase. We can see, but again, as we said, not 100%, but there's increasing pattern here. For example, this is outline way too high for a small SAT score, but higher GPA, and only few students have that pattern. So we have an increasing relationship between SAT and GPA. But here we say, although there's a substantial amount of variability in the relationship, so this will reduce our R value. The upward sloping pattern of the data suggests a linear model could be constructed. However, a great deal of variation in the model's error should be expected. Now, what percent of variation the final grade point average can be explained by the model relating to the total SAT score to graduating GPA? So that's our question now. Based on the data, what will be the R square? So the solution is using the least square method. The estimated method is given by the following. Again, here we can use the software to come up with a system. By estimating the GPA, this is what we have. And again, using the software, this is the result we get. Our goal is to find the R square. So when we look at R square, we can see that it's very small. So our conclusion here will be roughly 60% of the independent variable determine the dependent variable. The actual R value was 0.3996, so R square will give us 0.1597. Again, that's what we are looking for. There's a standard error of 0.4008. The total observation, which is the sample size, is 30. Then we do our regression. Degree of freedom is 1. The sum square. Then we have the mean square. Then we have the F score value also. And we may discuss about all this in our future lectures, especially when it comes to p-value, t-value, and f-value. These are hypothesis testing method, which we will cover in inferential statistics. Our main goal here is that, again, the R-square value is 0.1597. So that was our question. What is the R value? So this tells us that roughly 60% of the independent variable explain the dependent variable. And this is the scatter plot. We use the software. We can generate the equation. So this is our regression equation. This regression equation is based on the best fit line. And we use, again, Excel. We can use SPSS, so many software to do it. And this is the formula for the coefficient of determination. And in our next lectures, again, we're going to solve some problem. But before that, we are going to use the Excel and come up with what we just went through right now. Yeah, I'm going to just select some few values. I'll just enter some few values here. I want to have an increasing relationship here. So let's say this is our data set and it's two variables. And let's say our first variable is total expenses for advertisement. The second variable is the revenue generated by the company. So first thing I'm going to do is start with the scatter plot. So I select my data, then I'll click insert, and I'll look for the chart area, and I'm going to get scatter plot. So that's a scatter plot right here. So this is our scatter plot. And then we will right click on it. And then we look for trend. Okay, so that's it here, hard trend line. So I click on hard trend line, and this is again linear. So again, linear is already selected. And then I think that's it. So what I'm going to do now is to display the equation. So we can see that this is our data set. When we plot the data set, it seems like we have an increasing relationship. So our best fit line, again, this was done by the software, selected. And this is the regression equation, which also generated by the software for us. Let's see if we can make it bigger. Let's see. Increase the size. Yep. Now we can change the value. Let's change this value to maybe only 43, and change this to 40, and change this to 50, 60, and change this to 70, so that it will look more nicer. So we can see our best fit line again. And now you can see that as we change the value, the equation values also are changing, which is the slope. The slope is 39.5, and then y-intercept is 123. So with the software, again, very quick, take less than a minute, select my data, then I'll go to insert, then I'll select the scatter plot. Then when I get the scatter plot, I'll right click. Again, if you right click outside, it's hard, you can't find the trend line. You are looking for the trend line, which will generate the best fit line for us. So you come to the right click on the dot, and by that, you get the trend line. Then when you had the trend line, again, I already have it, but let's add it one more time. When I had the trend line, I will decide what model I want. Again, if I want exponential model, I will click on exponential. And now this time, the equation will be gone. It will give us different equation. But here again, we are doing linear, so linear equation. And that's it. So again, wish everybody the best. So in these lectures, again, we learn how to develop our best fit line. And also the most important thing is to evaluate that line. The best fit line is the line that are mostly have majority of the data around. And also this make it possible for the error value to be less, the less error value. So again, thank you for your time.